between you and lunch, so I'll definitely try and keep my remarks brief. We started the Wired and Wireless BU about 6 months ago, and it's been a very exciting 6 months. Some of it having to do with tweets and the like, but nonetheless, at this point we're firmly in deployment with 5G, and as you heard, that was led, of course, by South Korea, and we're really looking forward to the opportunities that we see coming from that rollout. Okay, so let me talk a little bit about how Xilinx is revolutionizing the 5G network. And we do it all the way from RF to core. And we're really the only company that can cover that breadth. Very few companies have the ability to do the type of RF that we do. And as I will talk about in a little bit, we're already deployed in a number of 5G networks at the moment. So in radio, we've always had strength in radio, but RF SoC is basically revolutionizing what's happening. And the reason has to do with a concept called massive MIMO. So massive MIMO is an array of antennas that allows you to beam, essentially, information to a number of different customers using the same frequency. It's called spectral reuse. And this is one of the key enabling aspects that allows the cost of 5G to be anyway tenable. So now, when we look at our current devices, basically, we're able to cover, say an 8x8 antenna with a single device. But with our new Gen 3 RF SoC device, which you can see outside, we have the capability to cover 16x16 antennas, so it takes 4 of them to do a 64x64, and it covers the entire spectrum from 6 gigahertz down, all with direct RF. So essentially, this is a radio in a chip. As I mentioned, we brought out our first generation of RF SoC about a year ago, and as I said, we're now deployed in 2 5G networks working very well. In fact, I believe we may have been the first device to carry 5G data at the World Cup over a year ago. So, with RF taken care of, we now talk a little bit more about beamforming. And beamforming is computationally very difficult. And this is where the Versal device comes in. We think that the AI engines are the ideal platform. It's the killer app, to some degree, for AI engines to do the type of beamforming calculations that are required. And we're really looking forward to showing that off over the next number of months. So, now I want to talk about a little beyond the radio. There's been a lot of discussion about baseband and ASICs potentially replacing FPGAs. From our perspective, we see ASIC replacement slightly differently. And that's the fact that we believe that ASIC will actually be replaced by disaggregation. So how is that going to happen? Essentially, what we're going to see is the traditional baseband that used to live beside the cell tower will be broken into 2 pieces. The first is called the distributed unit, and that's going to still live relatively close to the cell tower, and that's for types of applications that require low latency. And how will that function be provided? Well, it's going to be provided by commodity servers and FPGA accelerators. And who will provide the commodity servers? Well, people like AMD and that other company that they're gaining market share against. One of those will probably have the server. But we feel actually pretty confident that we are going to be the FPGA of choice to do the bit banging that's required, and that will always be required in that type of application. A little further away, we have the central unit. Again, this is not a data center like Salil talks about it with 2 kilometers of area. This is essentially a local office in which you have, again, servers being accelerated by FPGAs. So from our perspective, we see a very bright future in the ORAN standards that will be rolled out, and we think that there is an imperative as to why this will happen. It's already happened in data centers. We see the same thing happening in networks. Last but by no means least, of course, we play in the core network. This has always been a strength for us. This is where you have to actually build out the core now in order to take care of all of the data that we're seeing flowing from all these 5G devices. A lot of that, of course, is streaming video. And just some statistics for you. I think about 15% of the downstream traffic these days is Netflix and growing every year. So this gives you an idea of the demand that's going to be put on core networks. We recently announced our 56 gig SerDes device, which went to production this month. And next year we'll be integrating our 112 gig SerDes in Versal. Now we already demonstrated 112 gig 2 years ago, I guess, at OFC, and you can see it outside. So, go ahead and check out what that looks like. It's pretty impressive. Okay, so now what I wanted to talk a little bit about was a demo that we're doing, again available outside. And this is looking right at that radio problem that I talked about earlier. So if we look at this fairly complicated diagram at this hour of the day, nonetheless I'll try to walk you through it. We're looking at what's called a DFE, or a digital front end. Now the digital front end is really what its main purpose in life is to make life easy for the power amplifier. You see that sort of orange triangle on the right-hand side. That's where most of the power in a base station goes. So optimizing its performance is really important. So for the 5G example we're talking about, we would have liked to have used real user data. Unfortunately, we in the US are a little behind South Korea in our rollout. On the other hand, on 6G, we're doing remarkably well. Just want to tell you that. Nonetheless, we're loading 5G data into the memory on the left-hand side, and then we pull it into the Versal device, and we go into the fabric, the traditional FPGA fabric. And there we do a thing called crest factor reduction, CF4. And CF4 really just reduces the dynamic range of the data, and as I said, makes life a little bit easier for the power amplifier. Once we've gone through the CF4, we give the data a choice. It can go one of two ways. Both do exactly the same function, and that function is DPD, or digital pre-distortion. So it turns out that power amplifiers are inherently incredibly nonlinear, and as a result of that, if you operate them in their most power efficient way, they would really cause problems with the data. They would cause a lot of issues in terms of linearity. So what we do is a trick where we pre-distort the data going in so that from the power amplifier's point of view, what comes out looks linear. It's a nice trick. So as we say, we give the data two choices. You can go through the fabric, the traditional way of doing it, but then we also allow it to go into the AI engines, and we implement exactly the same algorithm. And this allows us to get a apples-to-apples comparison of what we see in AI engines versus traditional fabric. And to sort of cut to the chase, what I can tell you is the AI engines give us more than a 2x performance improvement relative to our 16 nanometer FPGA. And we do that essentially with about 40% less power than we would have had before. So we take the resulting signal, send it out through some A to D converters, into the power amplifier, and then we can see the result on the spectrum analyzer. And I would highly recommend that you go and see this outside. So, I think that's pretty impressive. But you may ask, right, so, who actually tests these things? Because the thing that actually tests these must actually be better than the device that's there. Well, another way of saying that, for those of you that have classical education, is quis custodiet ipsus custodes. How many get that? Who guards the guards? And essentially, we do. And because of that, we wanted to give you an opportunity to hear from a real expert in that area. I'd like to introduce Keysight Labs R&D researcher Nathan Jacobek, who will explain how this works on Versal.